Welcome to this number theory primer. In this lecture, we'll learn the proof of the fundamental theorem of arithmetic, which is, as the name suggests, a fundamental theorem in mathematics. And let us recall some ingredients that we need to prove it. So we will need Euclid's theorem, which says that if we have two integers a and b, not both of which are 0, so that their GCD exists, then their GCD can be expressed as an integer linear combination of the two numbers. All right. And we also proved the fact that if suppose we have three integers, and for simplicity, let us take them to be natural numbers, and suppose a and b are relatively prime, and assume that a divides the product of b and c, then in fact, a divides c. So we proved it, and we will need it in this lecture. Here are some problems for practice. This problem is star marked, not because this is hard, but because we are going to use it, and I've also supplied a hint if you are stuck. We'll use it at one point, and let's go ahead. So we will state the fundamental theorem of arithmetic very soon, but before that, let us prove a very simple fact. It says that every integer, at least 2, can be written as a product of primes. So this is intuitively obvious, because if I supply you an integer, let's say 38, you can always find a prime that divides it. So 2 is a prime that divides it. So you divide it by 2, you get 19, which is also a prime. So you write 38 as 2 times 19, and that's it. And you can do it with any integer, but let's see how to formally argue it. So basically the idea is, if you are given some integer at least 2, if it is a prime, you can celebrate. If it is not a prime, then one can write it as a times b, where both a and b are at least 2. Right? This is by the virtue of the fact that n is not a prime. If it were a prime, you could just say n equals n, and you have written it as a product of primes. So this is also counted as a product of primes. So n equals a, b, where a and b are both at least 2. And now a and b are both strictly smaller than n. So one can just keep going, and at one point one will be writing only primes. This process cannot just keep on going. But the formal way to argue it, let's look at that. So the formal proof would be, let b be the set of all natural numbers, at least 2, where n cannot be written as a product of primes. So b secretly stands for bad. So we have collected all the bad natural numbers, and by the well ordering principle, there is some, let's say m is equal to the minimum of all the bad natural numbers. So if b were empty, then we were done. Our goal is to really show that b is empty. So let me write that. Goal is to show that b is empty. So assume b is non-empty, and we'll produce a contradiction. So if b is non-empty, then it has a minimum element, and this is where we use the well ordering principle. Every non-empty subset of natural numbers has a minimum element. Right? So m is the smallest bad natural number, and if m is prime, so m basically cannot be prime. So thus m is not prime, because m is bad. Primes are not bad. M is not prime. And since it is not prime, we can write m as the product of two numbers a and b, where a and b are both at least 2. Right? So once we have that, now a and b are strictly smaller than m. Thus, a and b do not lie in b. And since a and b are both at least 2, this implies that a can be written as a product of prime. So a can be written, let me just say a is good. A is good. You understand what that means, and b is good. Since they don't lie in b and both are at least 2, they are both good. And product of two good things is good. That is something that we note, because if you have two good things, a and b, this can be written as a product of primes, that can be written as a product of primes. Therefore, their product can also be written as a product of primes. So since product of two good things is good, we see that m is also good. And that's a contradiction, because m was bad. M was the smallest bad thing. So that's the formal way to write it. At one point when you are comfortable with such reasonings, you do not write such things. But maybe when one is starting out, it is a good idea to write all the details. All right. Next is this lemma, which is immediate from the star mark problem. So it says that if a and b are relatively prime, and n is some positive integer, then a and b to the power n are also relatively prime. So in particular, a and b square are relatively prime, a and b cube are relatively prime, and so on. And this is immediate from the star mark problem. Basically, what you do is, or let you figure this out. This is not hard. Start with n equals 2 and then increase the n, and you can figure this out. Or look at the star mark problem at the same time. Wonderful. So now we are in a position to state and prove the fundamental theorem of arithmetic. It says the following. Fix an integer at least 2, and suppose we have primes p1 up to pk and q1 up to ql in increasing order. And suppose we express n as product of powers of these primes. Then, yeah, so we assume that each of these powers is at least 1, because otherwise, what is the point? All right, so the theorem says that actually these two seemingly different written representations of n, they are the same. So the same number of primes feature in them. In fact, the same primes feature in them, and they feature the same number of times. So if you express a natural number, at least 2, as a product of primes, there is essentially only one way to do it. You can shuffle around the positions of these primes, and you may write p1 cube as p1 square p, and so you can only make it look different in a superficial way, basically. So there is essentially only one way to decompose a given natural number, at least 2, as a product of primes. That is the fundamental theorem of arithmetic. So let's prove it. So first we will show that k equals L, and assume on the contrary, to prove this, assume on the contrary k not equals to L, and say L is greater than k. If k is not equal to L, then one is greater than the other. Say L is greater than k. Okay. So if L is greater than k, then there is something here which does not appear here. So basically, thus, there is some index j in 1 up to L such that qj does not appear in the list of p1 up to pk. So this is just a complicated way of saying that there is something here that does not appear here, simply because there are more things here. L is greater than k means there are more things here. Okay, now, then, qj is a divisor of, this is a trivial thing. Qj is a divisor of q1 to the f1 times ql to the fl, clearly, which implies qj divides n, which implies qj divides p1 to the e1 dot pk to the ek, right? And now we will use what we recalled earlier. If qj, so since qj is not equal to p1, or let's start in the other direction. Since qj is not equal to pk, qj is relatively prime with pk. In fact, it is then relatively prime with pk to the power ek by the previous lemma. And hence, by what we recalled in the beginning of this lecture, this implies that qj divides p1 to the e1 dot pk minus 1 to the ek minus 1. So what happened? Let me write one more term here. So what happened was, since qj is not equal to pk and qj and pk are primes, we see that qj and pk are relatively prime, and therefore qj and pk to the power ek are relatively prime by the previous lemma. And now, by what we recalled in the beginning, since qj divides this, it must divide actually the first guy. So it divides the first guy. But you can keep going. The same argument will apply to pk minus 1. And if you keep going, it will turn out that qj divides 1 dot qj divides 1, which means that qj is actually not a prime. A prime is always greater than 1. So that's a contradiction. So this is a contradiction. And therefore, our assumption that L is greater than K is false. Similarly, if we assume that K is greater than L, that will also be false. And hence we have established that K is equal to L. So thus, K is equal to L. And now, in fact, what we have really shown is that what we have shown is that this list is equal to that list. If you examine what we just did, you will see that not just K equals L, but in fact the primes in that list are exactly in the two lists are exactly the same, because that is all that we used. We just used the fact that Qj is different from each of the Pi's, and that's it. So we have a stronger conclusion. And let me just write a K here, because we have already shown that K is equal to L. So yeah, so this is what we have already established. And now suppose, so what we will show is that now we will show that Ek equals Fk. And again, assume Fk is greater than Ek, we'll produce a contradiction. So what happens is then n divided by Pk to the Ek, this is equal to P1 to the power E1 dot 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 Pk minus 1 Ek minus 1. This is equal to also Q1 to the power F1 dot 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 Qk minus 1 Fk minus 1 times Qk Fk minus Ek. And now we can repeat the argument that we did for n to this integer. This is an integer where here you see a prime Qk which does not appear here anywhere. This is a strictly positive number, and therefore there is a prime Qk which divides this guy, and hence it divides that guy, but that will give the contradiction that we saw in the previous argument. And therefore we cannot have this, and similarly we cannot have that. And hence our claim that Ek equals Fk holds. And you can prove it for each Ei, meaning you can show that Ei equals Fi for each I, and that's it. So that finishes the proof of the fundamental theorem of arithmetic. It's a very simple proof. It may look complicated because of all the notations. If you do not follow it immediately, I suggest you take maybe K equals 2 and L equals 3 and take some specific values of these numbers, and you will be able to follow the proof, but I don't think there should be any problem with the exposition as it is. Alright, so that's all that I wanted to say. As usual, like, comment, share, subscribe, and I'll see you next time.